Welcome to my 64th tutoring session in A-level chemistry. In this video, I'll talk about the absorption of UV and visible radiation by colorless and color compounds. And also, I'll provide you with the answer for the question, why compounds are colorless or colored. Now, there are four different types of electrons in organic molecule. They are sigma electrons, pi electrons, delocalized pi electrons, and non-bonded electrons. Now, the sigma electrons are present in saturated hydrocarbons like alkanes. Pi electrons are present in unsaturated compounds like alkenes, aromatic compounds, and carbonyl compounds. Delocalized pi electrons are present in compounds with conjugate system with alternative arrangement of single bond and double bond, as in case of 1,3-butadiene and 1,3,5-hexatriene. While non-bonded electrons are present in compounds containing heteroatoms with lone pair of electrons on the heteroatoms like oxygen, nitrogen, and halogen. So you'll come across non-bonded electrons in compounds like alcohols bearing the OH group, amines bearing the amino group, and compounds like alkyl or aryl halides bearing the halogen group with one or more lone pair of electrons. Now here is the order of energy required to excite the electrons from the molecular orbital in the ground state to the excited state. Now more energy is required to excite the sigma electrons, while least energy is required for non-bonded electrons present on the heteroatoms. Why is that? Let's find out. Now sigma electrons are present in sigma bonds, and sigma bonds are formed by endwise or linear overlapping of sp3 hybridized orbitals of the carbon atom, as in case of alkenes. And as a result, the sigma electrons are strongly held in the sigma bond, and more energy is required to excite the sigma electrons present in the sigma bonds. Now what about pi electrons? Now less energy is required to excite the pi electrons. Now pi electrons are present in the p orbitals, that is, they are present in the pi bonds, and the pi bonds are formed by sidewise or parallel overlapping of p orbitals, and this makes the pi bonds weaker as compared to the sigma bonds. Now in case of sigma bonds, the sigma electrons are strongly held because of linear or endwise overlapping of the sp3 hybridized orbitals. Well, in case of pi electrons that are present in the pi bonds that are formed by sidewise or parallel overlapping of p orbitals, and therefore the pi electrons in a pi bond are loosely held, and less energy is required to excite the pi electrons present in the pi bonds. So loosely held pi electrons in the pi bond require less energy as compared to the sigma electrons present in the sigma bonds. Now the sigma electrons are highlighted in red dots, while the pi electrons are highlighted in blue dots. Now in case of delocalized pi electrons, comparatively less energy is required than pi electrons. Now delocalized pi molecular orbitals are formed by continuous overlapping of p orbitals present on adjacent carbon atoms in case of conjugated systems. Now in case of organic molecules with conjugate system, as in case of 1,3-butadiene, you find p orbitals with odd electron on each carbon atom, and due to the presence of these p orbitals with odd electron present on adjacent carbon atoms, there is a tendency to undergo continuous overlapping. Now, because of the continuous overlapping of p orbitals, it leads to formation of delocalized pi molecular orbitals, and due to the formation of delocalized pi molecular orbitals, you come across delocalization of pi electrons in conjugated dienes. Now, as an outcome of delocalization of pi electrons, you see there is mobility or movement of pi electrons, and these pi electrons are therefore loosely held. So compared to the pi electrons, the delocalized pi electrons in conjugate system are very loosely held, and they can be easily excited, and it requires very less energy. So in case of conjugate system with alternative arrangement of single and double bonds, the carbon atoms with p orbitals bearing odd electron, there will be continuous overlapping between the p orbitals with odd electrons, and this leads to formation of delocalized pi molecular orbital, and that results in delocalization of electrons with increased mobility of electrons. As the electrons in the delocalized pi molecular orbital are already in constant motion, or the mobility is more, and therefore very less energy is required to excite the electrons. Now what about the non-bonded electrons present in heteroatoms? They require the least energy, because the non-bonded electrons present on heteroatoms like oxygen, nitrogen and halogens, they are very loosely held and freely available to absorb the electromagnetic radiation, so that they can get excited from the ground state to the excited state. Now the highlighting feature or characteristic feature of non-bonded electrons is that they are not associated with any atoms, and they do not indulge in any type of bond, and therefore they are called as non-bonded valence electrons. They are not indulged in any kinds of bonding, and they are freely available for the radiation to be absorbed. And that is how you end up with this particular energy order. Sigma electrons requiring the highest energy to undergo excitation from the ground state to the excited state, while the non-bonded electrons that are freely available and loosely held, they require least energy to undergo transition from the ground state to the excited state. Now the wavelength of the visible region ranges from 400 to 800 nanometers, while the wavelength of the ultraviolet region ranges from 200 to 400 nanometers. Now the visible region has a longer wavelength, while the ultraviolet region has a shorter wavelength. Now what about the energy? The ultraviolet region has the highest energy, while the visible region has the lower energy. Now these two parameters, that is wavelength and energy, they are inversely proportional. As the wavelength increases, energy decreases. As the wavelength decreases, energy increases. So energy and wavelength are inversely proportional. Now chromophores are covalently unsaturated groups like carbon-carbon double bond present in alkenes or aromatic compounds as unsaturated centers. So unsaturated centers with carbon-carbon double bond are present in alkenes or benzenoid compounds. They're also present in carbonyl compounds in the form of carbonyl group. They're present in azodides in the form of azo group and as nitro group in nitro compounds. When electromagnetic radiation of a specific wavelength strikes the chromophores within the molecule, the electrons within the molecule absorb the radiation, that is certain wavelength of radiation is being absorbed and rest of the wavelength is being reflected back, which when strikes the retina of human eye, it produces a characteristic color which is seen by the observer. So now we know why the organic molecule absorbs the electromagnetic radiation. Now, when does the molecule absorb the radiation? Now you know why the molecule absorbs the radiation. Now, when does the molecule absorb the radiation? When the electromagnetic radiation of a particular wavelength or energy, when it strikes the molecule, the electrons within the chromophore of the molecule, they absorb the radiation and undergo transition from the ground state to the excited state. Now, when does this happen? Now, this event happens when the difference in the energy between the excited state and the ground state is exactly equal to the energy of the electromagnetic radiation that is striking the molecule. So this is the first scenario. Now in the second scenario, energy will not be absorbed. So when the radiation strikes the molecule, energy will not be absorbed when the difference in energy between the excited state and the ground state is not equal to the energy of the electromagnetic radiation. Under such circumstances, the radiation striking the molecule will not be absorbed. So the energy has to match. When the energy matches, that is when the difference in the energy between the excited state and the ground state matches the energy of the incoming radiation, at that particular point, the radiation of a particular wavelength will be absorbed by the molecule. So here the energy levels are quantized. That is to say, when the incoming energy of radiation, when it is slightly lower or slightly higher than the energy difference, the electrons present in the chromophore within the molecule will not absorb the radiation. So energy levels are quantized, and that is why only when the energy matches, the radiation will be absorbed by the molecule. Now the energy equation, that is the equation for the energy of the electromagnetic radiation, is given by E is equal to h mu, where E stands for the energy of the electromagnetic radiation, h is the Planck's constant, and mu represents the frequency of the electromagnetic radiation. But the frequency is equal to c by lambda, that is c is the velocity of light and lambda is the wavelength of the radiation. And therefore, velocity of light will be equal to the product of frequency of radiation and the wavelength of the radiation. So I can find out the velocity of light by multiplying the frequency parameter with the wavelength parameter. And therefore, the energy equation gets reduced to E is equal to h c by lambda, because mu is equal to c by lambda. Now, this equation clearly explains the fact that energy and wavelength are inversely proportional. Now, when you observe the U visible region diagram, you can see that in the visible region, the wavelength increases while energy decreases. While in case of the UV region, having a shorter wavelength has higher energy. So wavelength and energy parameters are inversely proportional. So in case of visible region, energy decreases, wavelength increases. In case of UV region, energy increases, wavelength decreases. Now the excitation of electron is represented by asterisk symbol. Now the sigma to sigma star transitions are observed in saturated hydrocarbons like alkanes. N to sigma star transitions are observed in saturated compounds containing heteroatoms like oxygen, nitrogen, sulfur or halogen with non-bonding electrons. You will find this type of transition in compounds like alcohols, amines and alkyl halides. The third type of transition, that is pi to pi transitions, pi to pi star transitions, which is encountered in alkenes, carbonyl compounds and aromatics. Because you come across the pi bond in these class of organic compounds, and that is why you see the pi to pi star transition. And the last type of electronic transition is N to pi star transitions, which are encountered in carbonyl compounds and aromatics containing heteroatoms like in case of pyridine. So N to pi star transitions are observed not only in unsaturated compounds, but also in compounds containing heteroatoms, like in case of pyridine, which is both aromatic and also contains heteroatom nitrogen. Now visible region is a low energy region with longer wavelength, while the ultraviolet region is a high energy region with shorter wavelength. As you move from the UV region towards the visible region, energy decreases. As you move from the visible region towards the UV region, energy increases. Now there are certain compounds which absorbs only in the UV region, compounds like alkenes and conjugated dienes. So alkenes like ethylene and conjugated dienes like 1,3-butadiene and 1,3,5-hexatriene absorb in the UV region. And also carbonyl compounds like acetone and methyl vinyl ketone also absorb in this region. And the most common compounds encountered or the most common organic compounds encountered that will absorb in the UV region are the aromatic compounds or benzenoid compounds like benzene, naphthalene and anthracene. So this is about the compounds that absorb in the UV region. Now what about the compounds absorbing in the visible region? Now compounds that are generally colored will absorb in the visible region. So colored compounds absorb in the visible region. And why colored compounds absorb in the visible region? I'll explain later in the video. Now some of the example of organic compounds that absorb in the visible region that are colored are paranitrophenol and paranitrophenylene. They are bright yellow colored compounds. Natural pigments or biological pigments like carotene, lycopene and chlorophyll with extensive conjugation in their structures absorb in the visible region. And also synthetic dyes bearing the azo group also absorb in the visible region. Now the synthetic dyes, they absorb in the low energy visible region, and very less energy is required to bring about excitation of electrons in this synthetic dyes, because the common chromophore present in case of synthetic dyes is the azo group. Now azo group, they contain two nitrogen atoms, and a pi bond is connecting these two nitrogen atoms, and each nitrogen atom has a lone pair of electron. So as a group, it has loosely held pi electrons as well as very loosely held non-bonding electrons. And therefore, less energy is required to excite the electrons in the azo group present as chromophore in the synthetic dyes. And therefore, they absorb at a longer wavelength region, that is in the visible region. So sigma to sigma star transition, n to sigma star transition, and n to pi star or pi to pi star transition are generally observed in compounds that absorb in the UV region, because you can see the energy gap is so large between the ground state and the excited state that these compounds absorb in the UV region. So the energy gap between the ground state and the excited state is so large that this energy gap can be filled only by the high energy UV region. So the energy gap between electron orbitals in these compounds is too large to be excited by low energy visible light. And therefore, excitation of electrons in these type of compounds can be caused only by high energy UV light. So the difference in energy between the excited state and the ground state in these type of compounds or these class of compounds can be provided only by the high energy ultraviolet light. So what about the compounds that absorb in the visible region? Now compounds in the visible region, one common feature is the extension of the conjugated system. Now in case of paranitrophenol and paranitoaniline, you see that the nitro group and the hydroxy group, or the nitro group and the amino group, they are para to each other. They are complementary to each other, and therefore that leads to extension of the conjugated system. And similarly, as you move towards the right side, you come across the natural or biological pigments with extensive conjugation. You see nearly 11 to 13 double bonds in case of keratin and lycopene that are in conjugation, and therefore due to the extension of conjugation, the absorption of radiation will be of longer wavelength. And further, in case of synthetic dyes, the extension of conjugation is further favored due to the presence of lone pair of electrons on nitrogen atoms in the azo group as well as the pi electrons. Now in case of colored compounds, the energy gap between the ground state and the excited state decreases, and this small energy gap can be filled by the visible region. So the visible region has the sufficient amount of energy, sufficient amount of low energy that can fill up this small energy gap that you see in case of organic compounds, natural pigments and synthetic dyes. And therefore these compounds like organic molecules, natural pigments and dyes with extensive conjugation. So in these three class of compounds, you see alternative arrangement of single and double bonds with lower energy gap between the orbitals, allowing absorption of low energy visible light and producing characteristic color. Now it makes sense that visible region with low energy cannot bring about the excitation of compounds where the energy gap is more, because the visible region doesn't have the energy to fill up this large energy gap between the electron orbitals in compounds like ethylene, and conjugate dienes like 1,3-butadiene and 1,3,5-hexatriene. And also benzoate compounds like benzene, naphthalene and anthracene. But you may ask me, why can't the UV region, which is high energy region, bring about the excitation of electrons of compounds in the visible region, it is colored compounds? Why it is not possible, though it is high in energy? The reason is the energy levels are quantized. When the energy provided by the radiation, when it is slightly higher or lower than the required amount of radiation, the energy will not be absorbed. So the energy has to match. So whenever the energy matches, the radiation will be absorbed because the energy levels are quantized. So now we know why certain compounds absorb radiation in the UV region while certain compounds absorb in the visible region. Now visible region, wavelength ranges from 400 to 800 nanometers with longer wavelength and low in energy. Ultraviolet region, wavelength ranges from 200 to 400 nanometers. It has a shorter wavelength and of high energy. Now colorless compounds generally absorb radiation in the UV region, and some of the compounds that absorb in the UV region that are colorless are aromatic compounds like benzene, naphthalene and anthracene, alkenes like ethylene, conjugate dienes like 1,3-butadiene and 1,3,5-hexatriene, and even carbonyl compounds like acetone that are colorless also absorb in the UV region. And colored compounds, they absorb in the visible region whose wavelength ranges from 400 to 800 nanometers. And colored compounds fall under three categories. They are organic compounds, natural pigments and organic dyes. Now UV visible spectroscopy is a scientific technique which involves interaction between the UV and visible radiation and the molecule. And as an outcome of this interaction, a particular wavelength of radiation, either from the UV region or the visible region, will be absorbed by the molecule. Now, why compounds are colorless or white? Because compounds that are colorless or white, they do not absorb the visible radiation. The entire wavelengths striking the colorless compound, it is reflected back unabsorbed. So none of the wavelength in the visible region are absorbed by these colorless compounds, and the entire incoming wavelength of radiation, they are being reflected back unabsorbed, and when it strikes the retina of human eye, it produces a characteristic color and it is perceived as a particular color as seen by the observer. But in case of colorless compounds, as the wavelengths of a radiation, visible radiation striking the molecule, they are not absorbed, they are reflected back unabsorbed, and this reflected radiation, it strikes the eye and it produces white light. Because remember, white light is composed of spectrum of colors. So when the unabsorbed UV radiation, when it strikes the retina of the human eye, it is perceived as white light or white color as seen by the observer. So this is about colorless compounds. And what about colored compounds? Now in case of colored compounds, they absorb radiation in the visible region. So when the visible radiation strikes the colored compounds, certain wavelengths are absorbed by the colored compound, while the unabsorbed wavelength of radiation is reflected back, unabsorbed. And when this unabsorbed reflected radiation, when it strikes the retina of the human eye, it produces a characteristic color as seen by the observer. Now, for example, phenylazobutanaphthol is a orange red dye, and the characteristic red color of this compound is an outcome of the fact that all the wavelengths of radiation are absorbed by the colored compound except for the red color of specific wavelength that is reflected back as seen by the observer as a red color. And this is why certain compounds are colorless, while certain compounds are colored. And what about inorganic compounds? Now, inorganic compounds like table salt, they are colorless, while transition metals are colored, because in case of transition metals like copper or its salts, you see that they have unpaired d electrons, and these unpaired d electrons, they can readily absorb the visible light, leading to colored compounds. So the partially filled d orbitals in the inorganic compounds is essential for visible light absorption of specific wavelengths, resulting in a particular perceived color. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.